Hello and welcome along to Enfield Physics Tutor. Today I've got a video which is part 2 of the particle in a box theory. Make sure your maths brain is fully tuned and try to concentrate on what is quite difficult maths. Last time we began by considering a single gas particle moving only in the x direction and colliding with the orange wall of a cube-shaped box of length L. We considered using Newton's second law what force was exerted on that wall. This of course is very unrealistic, and so we introduced two more particles moving along the x direction but at different speeds to consider the contribution to the force produced by each of these particles, and we ended up with a fairly simple formula, except of course that this formula is going to go on for billions and billions of places, and that's a serious problem, which we solved by introducing something called the mean square speed, where you take all the speeds, square them, add them up, divide by the number of particles. We then substituted that in to our formula, did some more maths and ended up with this wonderful formula. If that quick summary of the first video left you as breathless as it left me, then perhaps you should take a few minutes to go and look at part 1. See the postcard up at the top of this video. Well, we need to make this a bit more realistic, don't we? Particles don't just travel in the x direction. In order to think in 3 dimensions, we're going to consider the x, y and z coordinates. In order to do this, we are going to consider u, v and w, which are components along the x, y and z direction respectively. So we now have a particle moving with velocity c in any direction, and from Pythagoras in 3 dimensions we can therefore say that that speed squared, c squared, is equal to u squared plus v squared plus w squared. And it's also true to say that the mean square speed is going to be equal to the mean square speed in the x direction plus the mean square speed in the y direction plus the mean square speed in the z direction. So far, it has been a little talked about fact that n is absolutely flipping enormous. And because of that, we can make some wonderfully useful approximations. In this case, that the mean square speed in all 3 directions is going to be the same. Now think about this for a moment. This doesn't work if you've only got a small number of particles, like say 100. But if you've got say a mole of particles, 10 to the 24 odd, then it's a very good approximation to say that these 3 speeds, or mean square speeds I should say, along the cardinal directions are equal. We can now say therefore that 3 lots of u squared bar is going to be equal to the mean square speed, which leaves us with 1/3 c squared bar equals u squared bar, and this is where the mysterious 1/3 comes from. At the end of the last video we arrived with this formula, which was for a number of particles all moving along in the x direction. We can now generalise this for a formula for pressure times volume for particles moving in any direction if we use this quantity known as the mean square speed, or c squared bar. And here you can see PV equals 1/3 n number of particles, m mass of a particle, times the mean square speed. We can almost see the mythical pot of gold at the end of the rainbow. Just one more mathematical concept, that of the root mean square. In this case, the root mean square speed is where we take the square root of the mean square speed, and we write this as CRMS. This therefore means that our pressure times volume formula becomes 1/3 nm root mean square speed squared. It can be very confusing trying to get your head around the difference between mean square speed and root mean square speed, but in many ways the only difference is that one is the square root of the other. It's worth pointing out that I've seen exam questions that kind of float backwards and forwards between the 2 versions of this, so it's worth just trying to be clear about which one you're being asked for and which one you're dealing with. Though this is the end point of the derivation in some of the textbooks, it seems to me that there's some more really exciting stuff that you can do with this, involving things like Boltzmann's constant, for example, and temperature, and you'll most certainly deal with that as well in class. Who knows, I might even make a video about it too, because it really is a fabulous piece of physics. But we're not done yet. There's one more thing we need to say. As with most areas of physics, this one too appears to be built on a tower of assumptions. Some of these are very straightforward, that particles move in straight lines, and they do so randomly. However, we also assume that particles obey all three of Newton's laws. Have a little think to yourself. Can you think where Newton 1, 2 and 3 apply to our particles in a box? We assume that within collisions there is no loss of energy, i.e. they are perfectly elastic. Next up, we have to assume that the time between collisions is large. Now this is an interesting one, because what it basically means is there must be a lot of space between the particles, which by itself therefore means that the gas cannot be too dense, because if the particles are close together, i.e. the gas is dense, then it won't be a long time, relatively speaking, between collisions. On top of the time between collisions being big, we assume that the time, or the length of time, I should say, a collision lasts is very small. In other words, the particle spends the vast majority of its life just travelling in a straight line at a constant speed across the box, stroke container, stroke classroom. An ideal gas is a gas which behaves in these 6 ways. And as the name suggests, an ideal gas doesn't really exist, it's an approximation. Such a gas, an ideal gas, will follow the 3 gas laws that you studied earlier, but additionally will also have an internal energy that is only made up of kinetic energy, i.e. movement. As I'm sure you remember, the internal energy also normally consists of potential energy, but since the forces between the particles is basically zero, we can say that so is the potential energy. We explained previously that if the pressure is too high, then the gas will no longer behave ideally. Notice that I spelled too incorrectly there. Naughty me. Last point then for today, that if the temperature of the gas is close to the boiling point, that means that the gas is going to be close to turning back into a liquid, and therefore, again, won't be behaving in an ideal way. Fabulous. Well, we've reached the end of this huge long derivation. I hope you guys found it useful and even interesting. Please don't forget to remember to share my video with as many of your physics colleagues who will listen, and don't forget to subscribe. All the best for now. See you soon.